All right, so welcome back. Um, Last time I introduced analytic functions, which are the main object of study in complex analysis. And now I'm going to introduce three more types of functions, which, well, they're all, of course, related to analytic functions, but these are just interesting things to think about, and some of them will appear later on. Uh, but we're going to get the framework set up so that later on when we interact with these functions, we'll already have a working knowledge of a little bit of the theory behind them. Okay, so without further ado, let me define a harmonic function. So this is a function which, what's the easiest way to write this? Has two partial derivatives, or I should say, we have different partial derivatives, has partial derivatives of order 2 that are continuous and satisfy. So let's call the function u. It'll be in variables. And it has to satisfy Laplace's equation, where this triangle guy is the Laplacian, which is given by the sum of the second derivatives of each of the components, or with respect to each of the components, rather. Okay, so any function u in several variables whose sum of second derivatives is 0 satisfies the Laplace equation. And we call such a function a harmonic function. Okay, so in today's lecture, we're going to restrain ourselves to n equals 2. And so I'm going to go ahead and just write x1 equals x and x2 equals y. Okay, so then Laplace's equation is then going to read d2u by dx2 plus d2 u by dy2 is equal to 0. Okay, so what can we say about these harmonic function guys? Well, actually, what I'm going to do is say something about analytic functions. If f, so remember we can write this as u plus iv, where u and v are both real functions of the two variables x and y, the real and imaginary parts of z. So if this guy is analytic, and u and v have continuous, I'll write the CTS, continuous second order partial derivatives, then u and v are in fact harmonic. So it turns out, by the way, that this second condition, or the second condition, having continuous second order partial derivatives, it's actually redundant. We'll show later on that if you have a function that's analytic, then those u and v parts, the real and imaginary parts, are in fact going to be smooth. Okay, so since f is analytic, it satisfies the Cauchy-Riemann equations. So that means that we have du by dx is dv by dy, and du by dy is minus dv by dx. Right? These are our Cauchy-Riemann equations. Okay, well then it follows that the second derivative of u with respect to x, well, we can take out one of those derivatives, and du dx is dv dy by the Cauchy-Riemann equations, and we can always swap the order of our partial derivatives. No equal sign there. And now I can apply this second Cauchy-Riemann equation. And so this is equal to, we get a minus sign and a d, we're going to have two y derivatives now. Okay, so then we add this guy back over and we see that it satisfies Laplace equation, thus u is harmonic. And rather than go through basically the same steps again, I'll just say that v is similar. Okay, so the other part of the harmonic function definition was this part here. So it's just in our assumptions, but again, that's redundant, right? It follows from the analyticity. Okay. So there is a relationship between u and v that I want to flesh out now. So if u is harmonic on d, so whenever I give the domain of a function, I'm going to assume that it's a domain in the technical sense. Right? That's just we're going to assume that throughout the rest of the lectures. We're always working on domains unless otherwise specified. And v is a harmonic function such that u plus iv is analytic. Then we say that v is a harmonic conjugate of u. Okay, so if I give you a harmonic u and you find a harmonic v such that u plus iv is analytic, then the v you have found is called the harmonic conjugate of the u that I gave you. Okay, notice if v0, let's say, is another harmonic conjugate, well, then we have, well, let me write it explicitly. We have u plus iv is analytic, and u plus iv0, so these are both analytic. The difference of analytic functions is analytic. So we have I, v minus v0 is analytic. But multiplying by a constant doesn't affect our analyticity either. So that implies that v minus v0 is analytic. But remember, we had that nice theorem last time that told us that a real valued analytic function has to be constant. Well, here we have a real valued function, which is analytic, so this implies that v minus v0 is a constant. So V is equal to V0 up to an additive constant. And so the harmonic or a harmonic conjugate of U is unique up to this additive constant. Okay. All right, let's see. I wrote down an example and then didn't give the function. Let me figure out which one it is. It's xy. Let's find a harmonic conjugate for this function xy. So first, let's show that u is harmonic, right? Well, second derivative, obviously is equal to 0 on both accounts. And well, moreover, 0 is continuous, right? Both of the partial derivatives exist and 0 is continuous, obviously. And so u is indeed harmonic. Okay, so to find the harmonic conjugate, what we do is we solve the Cauchy-Riemann equations. So we take du by dx equals dv by dy. What does this tell us? This tells us dv dy is equal to partial derivative with respect to x is y. And so this tells us that v must be equal to y squared over 2 plus a function of x. Okay, on the other hand, the Cauchy-Riemann equation du dy equals minus dv dx implies dv dx is minus h prime of x. So I'm taking the derivative here. And then on the other hand, yeah, okay. On the other hand, derivative of u with respect to y is x. And so this must be equal to x. Now I solve for h. So far, this is just a review of some pretty elementary analysis. And so what I'm left with is that v of xy is equal to, let's say, y squared over 2 minus x squared over 2 plus a constant. Okay, so when I put this together, I see that, well, the analytic function that these guys make is minus I z squared over 2 plus I c. So all I've done here is I've added u plus iv to get this guy. And this is indeed analytic. Okay. Questions so far? Okay. So the next type of function I want to tell you about is a conformal map. So first, let me say that the harmonic functions are going to come up again, I think next week, when we start talking about line integrals. But conformal maps now are maps that preserve angles. So if I have, let's say 2 vectors in the complex plane, they're separated by some angle. So I'll formalize this in a second. So here's my z-plane. when I map this over to my W plane, wherever this thing goes, maybe it goes over here, the angle between these two vectors will stay the same. Okay, so let me formalize that. I haven't even told you what a vector is in the complex plane yet. So let's let gamma of t equal x of t plus I y of t, where t is ranging from 0 to 1. So let this be a smooth parameterized curve. So keyword here, smooth. I want to be able to take whatever derivatives I want. I don't really need smoothness. I need only derivatives up to a certain order, right? But let's just assume smoothness for now. And I'll state what orders I need later on if I think it's pertinent. Okay. So let's furthermore let this terminate at z0 equals gamma of 0. Maybe the better word is begin, but I don't know. Gamblin uses terminate, so let's go with that. Okay, so the tangent vector to the curve gamma at z0 is gamma prime of 0 equals, well, it's just the derivative. And this is just derivative of the x term plus derivative of the y term evaluated at 0. The angle between two curves at z0 is, well, it's just the angle between the tangent vectors. Okay, so it's worth drawing a picture here. So suppose you have, here's some domain, whatever, and we have this curve gamma. Maybe it does something like this. And we have another curve. Let's say it does, so let's call this one gamma. Let's say it does something like this. We'll call this one gamma hat. This point where they intersect, we have two tangent vectors, one to the curve gamma and one to the curve gamma hat. And between those two tangent vectors, there's a well-defined angle. So this is sort of a way of giving you this is sort of giving you a way to define an angle between two curves at a point at which they intersect. And the way we do that is by looking at the tangent vectors to each of the curves. Okay. So here's the theorem. If we have a curve gamma, so we'll again say it runs from 0 to 1. So it's smooth, parameterized curve, blah, 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 terminating at z0 equals gamma of 0. And f of z is analytic. Then the tangent to the curve f of gamma of t terminating at f of z0 is given by this analog of the chain rule. In fact, I would even call it the chain rule. No equal sign. This is just multiplication. So you might even write this as f prime of gamma of 0, gamma prime of 0, just to make it clear that this is really just the chain rule. Okay, so I'm not even going to bother proving this because it's exactly the same proof that we went through last week. Yeah, last week. So yeah, no need to do it a second time. Okay, just know that this is true. And well, what does this say? So if I have a curve and I map it to another complex plane with this function f, well, what happens to the tangent vector to the curve? Well, what happens is well, it's the tangent vector of the original curve multiplied by this term here, f prime of z0, or f prime of gamma of 0. Right? And so we have a dilation of the tangent vector. Okay. Okay, so let me finally define what a conformal map is. So a function is conformal if it preserves angles. What does that mean? So we say G is conformal at Z0. So this is a local definition. If whenever gamma 0 and gamma 1 are two curves, all the usual properties. Well, let me write down an important one with non-zero tangents. Then the curves given by the composition with G they have non-zero tangents at G of Z0, and the angle from the tangents of those mapped over curves. So from the first one to the second one. If this is the same. This should not be a Z0, that should be a 0. I need to relive there. These also need a 0 instead of a Z0. Yeah, sorry, there were a lot of little small mistakes in my copy of Gamelin in this section. I'm not sure why. But yeah, so this maps from the interval from 0 to 1, so we should have a 0 in each of these places. Okay, so what is the conformal map? Well, it's defined locally at a point z0. We say that a function is conformal if when you take the tangent vectors to two curves at before mapping the curves over. And then after mapping the curves over, you get the same angle between these tangent vectors. Okay, and well, a conformal mapping of, let me write this down. A conformal mapping of D onto V is a continuously differentiable function that is conformal at each point of D. And that maps D 1 to 1 onto V. Okay, so we insert this extra assumption of injectivity into our definition of a conformal map. I don't have a reasoning for that. Let me think on that. Okay, but just as an example, z plus a constant, that's conformal. G of z equals az. That's conformal. How do we see this? Well, I take any curve, and now I take the derivative of this guy. I get well, what's so we need f prime of gamma of t, gamma prime of t, and then f prime is 1, so we just get gamma prime of t, right? So the tangent vector after mapping with f is equivalent to the tangent vector before mapping with f. And so, of course, if we have two paths and we take the tangent vectors, well, then the angle is going to stay the same. For g, derivative of g is just this constant a. So suppose I have two paths now, and I compute the tangent vectors at some point at which they intersect, and now I map them over. What's going to happen to the tangent vectors? Well, they both get scaled by the same amount, a, right? But this doesn't change the angle between them. Okay. Well, I should stipulate we do need a to not be 0 here. All right, so here's another theorem. If f is analytic at z0 and the derivative at z0 is not 0, then f is in fact conformal at z0. So here's the proof. So let gamma 0 and gamma 1 be two curves, both terminating at z0, right? And we'll assume they have non-zero tangents, all the things we need. By the previous theorem, so this is the theorem on the chain rule, essentially. The tangents to the curves f of gamma 0 and f, that's not enough, f of gamma 1 are obtained what we do is we multiply, well, let me just write it out. So we're just, again, multiplying by this this factor, I don't even know what to call it, the derivative of f. So the arguments of both tangents are increased by the same angle what angle, namely the argument of f prime of z0. So remember that argument was the phase portion and the polar decomposition of a complex number. So as a consequence of this, well, we get what we wanted. So this implies that the angle between them is preserved. So what happens is, because of this chain rule, we multiply by this derivative of f term, and what that does is it well, since gamma 0 of 0 and gamma 1 of 0 are the same thing, they're both z0, right? What that does is it adds this phase to our complex, or to our vector, well, to our tangent vectors here, right? But it's the same phase. And so when we take the difference, they cancel. Right? So the angle between these two vectors will remain the same. Okay. All right. So analyticity basically implies conformal. You just got to guarantee that the derivative at that point is non-zero. Don't want that. I want to do an example. So let's take w equals z squared. So I'm thinking about w as a function of z here. And I'm going to think about this as a function from the right half plane to the slit plane. Okay, what does this thing do? So for all theta, such that 0 is less than theta, less than or equal to pi over 2, w maps the sector defined as arg of z less than theta. It maps it conformally onto the sector arg of z less than 2 theta of twice the aperture. So how do we see this? Well, we take the derivative, or we use that chain rule formula, right? This tells us that what's the derivative of w? It's 2z, right? So we get 2 gamma of 0, gamma prime of 0, for some curve passing through z0. If I take another curve, I'll get 2 gamma, let's call it gamma tilde of 0, gamma tilde prime of 0. So this is W of gamma of t derivative. I should, well, we're evaluating at t equals 0. And so again, we see that the angle between these two guys will be the same as the angle before mapping with W, right? It's just because of this term here, we pick up a phase in both of these terms, and it's exactly the same phase because these are both Z0, and so they end up canceling. Okay, so exactly the same argument. Okay, so here's an important point. Orthogonal curves are mapped to orthogonal curves by a conformal map. We like orthogonal curves because they make up things like our coordinate systems, right? Um, the usual Cartesian grid, right? These are orthogonal curves, or we can draw it as a bunch of orthogonal curves, so on. Right? But also the polar representation. Right? We have these radial curves going outward. And we also have these angular curves, so these circles going around the origin. And these things are orthogonal to each other at all the points at which they intersect. And what's interesting is that there's a map that goes between these two in particular, and that is the exponential. I should say, so I do need to restrict this somewhat. We need so we have to restrict this because the exponential actually maps to the punctured plane, right? It doesn't include the point 0. And so the map's not going to be 1-to-1 if we include the entire complex plane on the left. So what we have to do is we fix this problem by restricting to imaginary part of z less than pi. So this is just a strip in the plane. Okay, so this exponential function has this nice property that it'll take us from our Cartesian grid to the polar coordinate representation. And we think about that as taking these orthogonal curves in the plane, which are rectangular, and map it to a bunch of circles and radial lines outward. So one of these things gets mapped to circles. I think it's the horizontal, and then vertical gets mapped to radial lines. I might have that backwards. Do I have time to figure it out? Not really. Okay. So we can maybe figure that one out later after we're done here. Okay, but let me introduce the last type of function I want to talk about. Which is called a fractional linear transformation, sometimes called a Mobius transformation. I am pretty sure we need these guys. I I can't remember. But what is this? So this is a function of the form W. Let's say W equals f of z equals az plus b over cz plus d, where a, b, c, and d are all complex numbers, and ad minus bc is not equal to 0. So I'll say more about this condition in a second. So notice that we can divide. We can essentially divide out this c here. So divide by c on the top and the bottom, right? This first term becomes 1. Then we get a d over c, a b over c, and an a over c. Well, we might as well just rename all of these a, b, and d, right? And my point is that we might as well have written az plus b over z plus d. Because the c is I don't want to say redundant. We can always get rid of the c, right? Just by dividing it out. So we might as well just set c equal to 1. Okay, so notice, let me tell you why this condition is here. Notice that the derivative of f is, well, you use your usual quotient rule. And this simplifies to ad minus bc over cz plus d squared. And one of the things that we wanted in all of our previous discussion was for this derivative guy to not be 0, right? And so the assumption that f prime is not 0 is equivalent to the assumption that ad minus bc is not 0. So that's why this is here. Another thing to point out maybe is that if we scale, well, I mean, I sort of already pointed that out. This is just a different way of phrasing what I was talking about earlier. So if we scale each of these things by some constant factor, so call it w, well then all the w's cancel, right? Okay, so some examples of fractional linear transformations that we'll give a name to. So for c equals, I should amend something I said earlier. We can only do this when c is non-zero, right? When c is equal to 0, which is the case I'm about to talk about, this gives us an affine transformation. It gives us something of the form az plus bb, so az plus b. And I have thrown away this extra d because, again, the d can be absorbed into these constants just by redefining them. So when a is 1 and c is 0, then what we have is something of the form z plus b, and this is a translation. We all know what a translation is. When c is 0 and b is 0, this gives something of the form az, which we call a dilation. And when a is 0, d is 0, and b equals c equals 1, well, we get 1 over z. And this is called an inversion. Okay. So, and what follows, we're going to think about we will think about F as a map from the extended complex plane to itself. What does that mean? It's the complex plane including infinity. And so I think I should really take a second to explain what that looks like topologically. So when you take the complex plane and you add infinity to it, what you're really doing is you're taking your plane and let's say there's some boundary outside here, which we'll call infinity, right? And you're identifying that entire boundary with some point, right? So the point is infinity, right? So this entire boundary is getting mapped to this point, right? And so what you have is, well, the plane starts wrapping in on, wrapping itself upward, and the boundary gets identified with that point. So what you have is a sphere. Okay. And the reason I explain this is because we're going to talk about lines that pass through infinity, and these lines are going to be referred to as circles, right? Because when I have a line that passes through infinity like this, well, these 2 points get identified, and so what I have is a circle, which maybe looks like, well, maybe like this on the sphere. So a line in the extended complex plane will be nothing more than a circle that passes through infinity. Okay. So some things need to be pointed out. If F is affine, we define F of infinity just to be infinity. So the thing you would expect, right? I have AZ plus B, I plug in infinity, I would expect infinity out, right? Otherwise, F of Z has the form AZ plus B over CZ plus D with C not equal to 0. So again, we could just get rid of the C. Right? And F of minus D over C is defined to be infinity. So plug in minus D over C, this guy goes to 0. Right? So this is, again, the thing that we would expect. And we take F of infinity to be equal to the limit as E goes to infinity of the fractional linear transformation, which is just going to be A over C. Okay. Other things maybe should be pointed out. I mean, they're kind of obvious, given all these definitions. Translations map infinity to infinity. So do dilations. They're both affine maps. While inversions map 0 to infinity and infinity to 0. So again, the thing that you would expect. And maybe not pertinent to us at this moment, but still interesting, is the following. The inverse of fractional linear transformation, maybe I'll start calling them Mobius transformations just because it's easier, has this form. And we'll notice that it's also a Mobius transformation. We also have that the composition of 2 Mobius transformations Um, uh, okay, actually, I will write it out. Um, so I'm taking f to be az plus b over cz plus d, and g to be alpha z plus beta over gamma z plus delta. Right? So when we compose these things, we'll get a alpha plus b gamma z plus alpha beta plus b delta over c alpha plus d gamma z plus c beta plus d delta. Okay, so if you compose these things and you do all the tedious simplifying, then this is what you get. Right? And moreover, we have an identity element, right? Just f of z equals z. That's a Mobius transformation, right? A equals 1, d equals 1, b equals c equals 0. So also composition of functions is associative, right? That's a given. So what we have here is a group. So we have that Mobius or fractional linear, whatever, transformations form a group. And even more interesting, there's a map. So the map phi taking, let's say, an arbitrary Mobius transformation here, taking this guy to the matrix A, B, C, D, this is a group homomorphism. So on the left, we have composition of functions as our operation, and on the right, we have multiplication of matrices as our operation. Okay. You can show that this is actually a group homomorphism, and this is maybe made most clear, well, okay, it doesn't make the homomorphism probably more clear, but this is nice because that condition AD minus BC not equal to 0 that we specified earlier for the Mobius transformation, well, this is just saying that the determinant of the corresponding matrix is non-zero, and so this guy is invertible. Right? Okay, so this is yeah, okay, all right, I won't say more about that. So now I want to either state or prove a few results. The first one I'm just going to state because I don't really have time to prove it, and the proof isn't really that enlightening anyway. I'll do an example just to illustrate it, but basically, given any z0, z1, z2, and w0, w1, w2, there is a unique I'm going to say Mobius transformation. W equals WZ such that WZ0 equals W0, W of Z1 equals W1, and W of Z2 equals W2. So if I give you 3 points and you come up with 3 values for the function, well, then this completely defines the Mobius function. It's unique. Okay, so just as an example, we'll give the engineer proof by example. Okay, so suppose I have these 3 conditions. So I send -1 to 0, infinity to 1, and I to infinity, and we'll define WZ. So we'll drop that C, right? Because we know that it's irrelevant. So we'll take w of -1 to be, well, what is that? That's b minus a over d minus 1. And we want this to be 0. We solve and we get a equals b. We plug in I, we get ai plus d over I. Oh, no, sorry, that should be an a now. A is equal to b. I plus d. And I want this to be infinity. Right? And the way to get this is by setting d equal to minus I. Okay. And then w of infinity, I want to be equal to 1. And how do I get that? Well, the limit is a, right? And so I just set a equal to 1. So the w z I'm looking for is completely determined. It's z plus 1 over z minus I. Okay, so that's the point of the theorem. I'm not going to go through the details of proving it. We won't really learn anything from that. But let me move on to the next theorem. So this one is pretty simple to prove. So I'll call it a Mobius. Every Mobius transformation is a composition of dilations, translations, and inversions. Okay, very easy. So let's take as the first case, if w maps infinity to infinity, so then the function is affine, right? With a not equal to 0. But this is just, so how do we get this? We map z to z plus b over a, and then we map that to a times z plus b over a. This first guy is a translation, and the second guy is a dilation, right? And that's just equal to az plus b. Okay, so checks out. And now on the other hand, if w of infinity is not infinity, so let's say it's finite, then we have the more general form, az plus b over cz plus d. I'm going to get rid of the c again. We don't, yeah, redundant. And well, az plus b over z plus d is a plus b minus ad over z plus d. So multiply this guy by z plus d over z plus d, and you'll see that you get exactly this. So how do I write w? Well, I take z and I map it to z plus d, and then I map it to 1 over z plus d, and then I map that to b minus ad over z plus d, and then I map that to a plus b minus ad over z plus d. So this first guy is a translation. This second guy is an inversion. This third guy is a dilation. And this fourth one is another translation. Okay, so that completes the proof. So every Mobius transformation is a composition of dilations, translations, and inversions. Okay. All right. So the last thing I want to mention is a theorem. It tells us that a Mobius transformation maps circles in the extended complex plane. So remember that includes lines. Yeah, to circles. All right. So this will be our last thing today. Let's go ahead and prove this. So it suffices to establish the theorem for translations, dilations, and inversions, right? Because we know from the previous theorem that every Mobius transformation is a composition of these things. So if I take something that maps a circle to a circle and compose it with another thing that maps a circle to a circle, well, then I've just mapped a circle to a circle, right? So we've narrowed it down to translations, dilations, and inversions. But translations very clearly map a circle to a circle, right? What does a translation do? It just takes my circle and shifts it in some direction, right? Depending on what you're translating by. Okay, so that one's already done, right? What does a dilation do? Well, it either stretches or compresses my circle, right? But at the end of the day, I still have a circle. Because what can a dilation do to the angle of a point on that circle? Well, it just rotates it, right? But if I rotate all of the points in the circle by the same amount, well, I still have a circle. So again, the dilation is very easy to see. And so we've narrowed it down actually to inversions. So all we need to prove is that inversions will map a circle to a circle in the extended complex plane. Okay. So we consider WZ equals 1 over Z. All right, so first, assume the circle does not pass through infinity. Okay, so it's a circle in the usual sense in the complex plane. It's not a line. Well, then we could define it by, it is defined by some equation of the form z minus a modulus squared equals r squared. So a is some complex number, and r is the radius, so that should be real. And r should be greater than 0. Then the image of the circle, so this w guy, satisfies, well, w, well, z is 1 over w, so we have 1 over w minus a modulus squared equals r squared, which is equivalent to 1 minus aw modulus squared equals r squared times the modulus of w squared. And well, this is equivalent to, so 0 equals 1 minus aw modulus squared minus r squared modulus of w squared. And remember that the modulus squared is just the number times its complex conjugate. And so multiplying this whole thing out, we see that this is equal to the modulus of a squared minus r squared times the modulus of w squared minus aw minus aw conjugate plus 1. So now we'll let w be u plus iv, right? W is a complex number. We can split it into its real and imaginary parts. Right? So nothing special going on here. U and v are real. Well then, so this equation now transforms to modulus of a squared minus r squared And then u squared plus v squared, that's this modulus of w squared, plus some constant times u plus some constant times v plus 1 equals 0. So these constants are coming from plugging in u plus iv for the w's here. Okay. So if r is equal to the modulus of a, this is a straight line. Which is a circle through infinity. Okay. On the other hand, if r is not equal to a, modulus of a, then all you got to do is complete the square. And you'll see that you have an equation for a circle. Okay. Okay. It's not worth doing a whole bunch of extra work. So I'll say, so we assumed up here at first that the circle does not pass through infinity. And I'll just say that if we consider a circle passing through infinity, so that this is, remember, really just a line, then it satisfies cx plus dy equals e for some constants c, d, and e. And so you can do a similar calculation that we to the one we just did, and we'll find again that well, what you'll find is that the image is a circle in the usual sense for e not equal to 0, and a circle through infinity, or a line for e equal to 0. And then that would complete the proof. Okay, so these Mobius transformations have this nice property that they take a circle in the extended complex plane, including these straight lines that touch infinity. They take each of those circles to another circle in the extended complex plane. Okay, I'll go ahead and stop there. Any questions? One second.